Hi, my name is Arnold Elgqvist. First of all, thanks to Bearing News and Keenan Özkan for inviting me to this event. There are so many things I would like to tell, but I have selected a very dear concept for me, that is the bearing reliability assurance. Uh, it's very good if it BRA, it's bra, that's good in Swedish, so it's fit very well. So this is a new concept. I believe I has it as a roadmap to bearing total reliability. And it's a new mindset, a new way of thinking, plus objective. We're going for zero failures of bearings in the industry, in the equipment. Applying the following strategy: defect elimination at the beginning to start with, then precision maintenance, condition-based maintenance, and to end failure, root cause failure analysis. Let's start with an exercise. Comparison of the cost for different strategies of maintenance. You know, the three different strategies. We have bearing failures in a centrifugal pump in a refinery. The mean time between failure is 4,400 hours, more or less 6 months. Cost for the lost production, $25,000 per hour. And a complete set of replacement parts, bearings, mechanical seal, and labyrinth is $6,800. So we will calculate the total cost for 3 years. We start with the corrective maintenance, downtime of 48 hours, 2 days. Yes, due to if it goes to catastrophic failure, we will have damage on the shaft and in the housing, and these will have to be repaired for a cost of $20,000 as additional cost. So if we have failures 3 times a year, we will have twice a year, we will have 6 failures during these 3 years. And if we look at the cost, it will end up at $7,360,000. Let's go to the preventive maintenance. We will apply this every 3,800 hours to be sure that no failure will occur. The stops will be for 8 hours, and a complete set of replacement part, of course, will be used as always in preventive maintenance. So now we will have to do it 7 times, and we will end up with a cost of $1.4 million. So the predictive maintenance. Well, if we have a mean time between failure of 4,400 hours, they may detect it at 4,200 hours. So it will be 6 times. The stop time will be reduced to 6 hours only, because if we avoid failure vibrations, the mechanical seal may still be okay, so we will only change bearings and labyrinths, the seals. Will have a cost of $1,000. So 6 times the cost will end up as only $906,000. What do you think about this? Are you okay with this? You shouldn't be, because this is totally wrong. Why? We need to change the mindset. We must think different. Let's be proactive. Why should we accept the MTBF of only 6 months, 4,400 hours? Can't we change that? Can't we avoid these failures? Let's look for the root cause for the failures of these bearings instead. Determine and implement the required corrective actions. These kind of pumps usually are designed to last for 5 years. The bearings are for 5 years. So 6 months is completely wrong. So we will not accept these failures, this MTBF. If we look into the ISO 281, that is used to calculate bearing life, the version of 2007 indicates under certain load, a modern bearing of high quality may reach an infinite life. Yes, an infinite life, as long as the conditions of lubrication, the cleanliness, and other operational conditions are favorable. Oh, what a challenge! Is it in utopia? It sounds incredible. Can it be possible? Well, we said the same. I say we because at that time when this was going to be implemented, I was a quality manager in one of the SKF factories. And I said, this is incredible. But then we started to talk about zero defect in the in manufacturing processes, and we made it happen. How did we achieve zero defect? Instead of quality control, that means being policemen, we changed over to quality assurance. Just the way how to assure that we would have the quality 100% with zero defects. And we achieved it. 2 years afterward we started this, I was lucky to receive an award for zero defect from a Nissan plant. So let's do the same with the life cycle of bearings. We must focus on defect elimination from the real start point, the design, to the very end. Precision maintenance, precision lubrication, alignment, balancing, and so on. Then the new opportune condition-based maintenance to detect not initial failure, but symptoms of defects that may lead to bearings failure. This means we should look for symptoms of defect before they have caused any damage to the bearings. Then the proactive maintenance to deal with initial but irreversible failure. Then these failures are that we cannot avoid them. And when we at the very end have the bearing failure, we should perform a bearing failure root cause analysis, just to learn how to avoid this failure in the future. I talk about bearing failure. What do we mean? It should be considered as a failure of a bearing when this no longer complies with the required performance. And this may be very different. For example, if we're talking about the machine tool spindle, where as soon as the bearings lose the rigidity, the machine quality will decrease. If we have a fan, air conditioning, the noise, vibration will indicate where the bearing has failed. But if we go to the mining industry, in a conveyor, as long as these bearings rotate, they are okay. So it's very different depending on the application. So, would you not prefer to avoid failures instead of detect failures? Let's look at the life circle as Arsene Blitz and published by Reliability Web. We start with the design of the equipment. And there we should select the bearing, which should select its lubrication. And then we come to the installation, the fits, the mounting, and the installation of the equipment. Next, we start up the equipment, and then we should go on with condition-based maintenance, looking for the symptoms before irreversible failure has occurred. And if we really are efficient, why shouldn't we have achieved a longer life than expected? Well, if we have the potential failure, we detect it by any of the predictive maintenance technologies, then we must look for why do we have this? That proactive maintenance, we shall program, we should make a diagnosis, what is the cause, and how long will this bearing still work before we have a catastrophic failure that we must avoid because all the collateral damage that this may cause to the machine, to the equipment. So at the end. So functional failure, okay, may occur, but it should not be a catastrophic failure. So we have 5 different target areas. We have the design area, where we make a deep review of the design, the bearing selection of the bearings, applications, and their lubrication. The installation, here we must start with the fits, mounting method and tools, and the installation of the equipment itself. Then the interval IP between installation and the potential failure, where we must apply precision maintenance and use the predicted technologies to detect symptoms, as I said before. Then when we get to the P point, where we have a potential failure, we have an irreversible failure that sooner or later will make the bearing fail. There we apply the traditional proactive maintenance, analyzing why and determine the corrective actions, which should be confirmed by the failure root cause analysis after the functional failure, after the bearing has been dismounted. Well, here I want to add an additional change of mindset. We must look at every equipment as an individual. So many times I've noted that we expect by mistake that all equipments that are the same should have the exactly same operating conditions, the same temperature, the same vibration level. This is impossible because they are so different. There are different tolerance and so on inside this equipment. Yeah, the same as human, there are different characteristics. If we look at equipment, they may have different operating temperature, different noise level, different vibration levels, different energy consumption, different reliability levels. The same as human beings. We may have different cholesterol level, different glucose level, different blood pressure, different energy consumption, and different levels of reliability. So we should not look to have all the equipment working the same. There are differences. So detecting failures does not improve reliability. It just reduces their consequences. So we must work on this and look for new opportunities to avoid these failures as much as possible. So if we go to the design area, where the equipment is designed, couldn't we, for example, look for optimized bearing, optimized lubrication as such, and optimize the reliability level of those bearings more than what's required to really have a first-class, very competitive equipment. An example, an electric motor, 800 RPMs, bearing on the transmission side, belt transmission, 6006 deeper ball bearing, normal conditions, and compared with the gen new 306 cylindrical roller bearings, optimized conditions. So, normal conditions for the 6306 with a lower carrying capacity will only give us 48,000 hours. Compared with the NU 306 with much bigger, almost double carrying capacity, optimized lubrication, optimized cleanliness, and we have, in fact, an infinite life bearing, according to calculated by the ISO 281. So how do we perform defect elimination by design? We have to select the correct bearings. We could optimize or we could just go for normal, depending on the application and the requirement. So we have to go through all the criteria for the selection, look for if or each and every one, if which apply and which does not. In my experience, the lack of knowledge of bearing designation systems is the second major root cause for premature bearing failures after lubrication in the industry. Look at this designation, a 6205, 2RS1 and RTN9 P63 LT20C VB123. It's a very special deep ball bearing. If you replace this by a 6205 set, it won't work. Another example, a spherical roller bearing 23064 CCK HA3084 S2 W33. Also an SKF designation. This is a high precision spherical roller bearing designed for the paper industry, for paper machines, modern paper machines that we are able to work at least 100 kilometers per hour. If you don't use bearing with a CO8, that is more than P5 precision, it won't work. I had one customer, they used two bearing in a cylinder with normal precision. And when they reached 80 kilometers per hour, they had to stop. They couldn't go further because the machine started to vibrate because these bearings didn't have the required precision. Another example from a refinery, they used two single row angular contact ball bearing in a pump, in an API pump, but they used bearings that were not prepared for mounting. They were missing. When I made the analysis, I saw the designation. I was afraid not to be able to see it, but if you see at the right, I could see the only designation, the suffix was MP, the UA for FAG, indicating preparation for mounting in pair was missing. So these bearings were preloaded internally, heavily preloaded, and you can see how the inner ring was completely deformed, sticking out. That moved the shaft, and the shaft destroyed, this movement destroyed the mechanical seal. And this caused the close down of 1/3 of a refinery for 3 months. Just the lack of 2 letters in the designation. So how long should bearing really last? Bearings from modern manufacturers, from quality manufacturers, are in very few cases present quality problems. They use quality assurance based on 0 defect, as I mentioned before, and faults are measured only in part per million. Previously, bearings failed because the material was not the quality as today, the design, the manufacturing quality. But now, the majority of the bearings fail due to external causes. So, bearings are innocent until the contrary has been proven. Well, an exception I have to mention are the fake bearings. These, of course, have not the quality as the brand they presume to have. The above should lead us to a positive and proactive attitude. We should see every bearing failure as a challenge, not as a problem. A challenge to identify the root causes and take the appropriate proactive actions to prevent recurrence of the same failures. How should bearings be handled? They should be handled as precision products and must to avoid damage. For example, if a bearing, even if it's in its package, falls on the floor, there may be damage inside because impacts on the ball's hurt. I believe you are agree with me on that. So the storage is of the bearings is most important. But the warehouse had another uh, responsibility. It must perform receiving inspection to ensure that the products really are the one that the users have been asking for. Second, bearings must remain as virgins in their original packages until their mounting. I show these photos from one of my customers. I recommended these bearings to be scrapped. Does this inspire reliability? Look at the packages. What can you expect from these bearings in the bearings inside these packages? We should look at the importance of correct lubrication. All the statistics I've seen in the last years indicate at least 50 or 55 in. I've seen the statistics up to 70% talking about the incorrect lubrication as a main failure. Here, this statistic is from FAG indicating 55% of the fails are due to lubrication problems. Degraded lubricant, incorrect lubricant, lack of lubricant, there should be a mix of lubricants, and so on and so on. So when we select the correct lubrication, we must include the correct lubricant, the correct lubrication system. The lubricant should be applied on the correct point, on the correct place. The quantity should be correct. It should be applied at the correct time, and we should have the correct people to do it. They should be trained. They should be so-called tribologists. So now we come to the installation. Here we have to look first on the fits. The importance, if we have too loose fits, the bearing will move and it will damage the shaft and the housing. It will result in heat, corrosion, adhesive wear, fractures. If we go to the opposite, we have excessive interference fit. This will reduce the internal clearance even up to preload, and we will have increased temperature, fracture of the rings, and so on and so on. Look at this interesting example I got from one customer. If you look at the outer diameter, you can see the smearing indicates that this bearing was rotating in the housing, the pillar block. It was rotating. Why? Well, if we look onto the raceway, we see that both rows of balls are marked all around the bearing. And that can only happen when you have a preloaded bearing. So the preload caused higher friction, made the bearing rotate in a housing that, of course, had a loose fit, the G7 tolerance, yes, to allow the actual displacement if it's it's a floating bearing. Yeah. So is it typical failures? You can see both indicating the same mistake. Mounting is very easy to do, avoiding mistakes. It's so easy. There are a few golden rules you should follow. And one of them I want to indicate here is that you have to ensure that the mounting force always is applied to the ring that is to be mounted. Then you will avoid any damage to the raceways and rolling elements. Even when you install the equipment, you have to avoid any impacts or forces onto the shaft, because those will also go to the bearing, to the fixed bearing, and cause damage inside. Now we go to the interval IP, the proactive area. Now we will use the predicted technologies to detect symptoms of defects previous to potential failures, just to have the opportunity to correct these defects in time before they cause any damage to the bearing. So these will continue to live on. And we should apply precision lubrication using, I recommend, ultrasound. In this area, there are still no irreversible damage to the bearing. So we may apply precision maintenance, as I said, yes. Which are the technologies that are capable to do this work for us? The traditional ones: vibration analysis, oil analysis, ultrasound, and thermography. But don't forget precision lubrication. Remember the 55% of failures due to lubrication problems. And here I once again recommend the ultrasound. We shall never be happy with the result. There is always, we can always keep on improving. The never-ending improvement. This is an example from a plant in the USA. Maintenance started to do vibration condition monitoring, and they made the vibration levels go down to what they considered normal. You can see the values of 0.15 for the slow pumps, 0.26 for the high-speed pumps, and for the fans, 0.338. And you can see the costs. But they thought, can't we reduce the vibration level even further? So they analyzed these vibration levels to find what was causing the vibration. So they found exactly what to correct, and they were able to get down even further in the slow pumps, even to the 10% of the earlier value, and the maintenance cost went down to $2,600. The high-speed pumps, they could also reduce it to 1/10, and look, from $46,000 they went down to $2,500. Yes, lower vibration made this mechanical seal that's the most expensive, they last much longer. Fans, they took it down to 0.052, and they got the cost of $226. That's just only the predicted maintenance and lubrication cost. So they got down to $5,300, $400. So they were very happy presenting, we have reduced the maintenance cost $68,000. But they forgot one thing, the most important. If they got the maintenance costs so much lower, that means that much must have meant that the downtime due to maintenance must have been much reduced. So what the additional value of the production they achieved? Yeah. The availability of the machines must have increased a lot. So ultrasound, we can use it for lubrication problems. We can see whether lubricating film is being reduced, excess or lack of lubricant, wrong lubricant, or contaminated lubricant, particular contamination, and in an initial stage and the overloads. Vibration analysis, yes, we should not look for initial bearing failure, but abnormal vibration that may indicate defects that can lead to bearing failures. We should look for higher vibration levels than normal for the corresponding type of equipment. These vibrations must be analyzed to determine the specific sources of these vibrations to achieve the same as they did in the plant I mentioned in the USA. Oil analysis also can detect defects that can lead to bearing failures, as particular liquid contamination, degraded oil, wrong viscosity, or depletion of required additives because they are consumed over time. Thermography, overloads, misalignment, transmission of high temperature, mounting problems, wrong bearings. But talking about temperature, please bear in mind that an increase of the operating temperature most times appears in a late stage when the potential failure already has occurred. Or that means it is irreversible. The bearing will fail over time. This is a very interesting example of thermography. Can you see any problem with this transmission? I can't. But if we look through thermography, oh yes. Overheating at one side, there is a misalignment. And if it's corrected in time, okay, this machine, this fan will keep on working. So now we come to the corrective area. We have had the P, the potential failure, and now we should look to be efficient to analyze why did we have the failure, how long will the bearing last, just to avoid the catastrophic failure that will have collateral damage that will cost a lot of money, not so much by repair, but as lost time. So we should close the circle to assure the very best results. We should detect on time, analyze, just to look for what are supposed to be the root cause for these failures. And we shall apply them, but please don't stop here. Many times they stop here and say, now we done it, we changed the bearings, we changed the lubricant, we changed this and that. But that's not true. We must make the follow-up, review the results of the corrective action. Did we really have the expected result? Did the temperature go down? Did the vibration go down? And so on. We have to close the circle. Yeah. When we get to the function failure, okay, the bearing is dead. But we must avoid this failure to happen again. So now we have to do the root cause of the bearing failures. And these are again the different failure causes. As I showed before, in this case, according to FAG. Look for the manufacturing defects, less than 1%. It may be only ppm, yes? Incorrect bearing, 20%, I have that in second place. Here I have contamination in second place. That depends, yes? But my experience is incorrect bearings at number 2. When we come to bearing failure analysis, the most important thing is to have the information before the analysis. As much information as possible, photos, all the information as possible. Remember, now you are doctors. You are going to analyze a dead corpse. Why did he die? This example is in a photo I got from one of my customers. And he said, this bearings failed after only 15 days. Can you tell me why? First, I got angry. I was going to answer with a mail, do you believe I'm a magician? But then I cooled down and I sent him my format on all the information I require to do a real professional and exact failure analysis. If we're looking into the ISO 15243, these are the failure modes they indicate: fatigue, wear, corrosion, electrical erosion, plastic deformation, fracture, and cracking. And they show a lot of very extremely good photos that they have collected from bearing manufacturers and so on to show how they look. And these photos, I recommend use them to identify what really, is it this kind of failure or is it another? They are very good photos. I recommend them. So if you're going to make a complete failure analysis, you should include the following. As I said, the most complete information. Prepare an inspection sheet to capture all the observation. Remove sample, use a lubricant, look at the lubricant. Once I got bearings for failure analysis, but the customer washed them. I couldn't find the lubricant. That's so important because I remind you again, 55% of the failures are due to wrong lubrication. And then we want to look at the lubricant. In what condition, which condition is it? It may tell you everything. So look at a sample of the same of the same new unused lubricant. How did the grease look in the bearing? How did the new grease look? Verify the environmental conditions. Disassemble the equipment. Look at the bearing before dismounting them. Do they rotate? Are they still in their place? And so on. Inspect the condition of other components. Mark, very important, mark and record the position of the bearings and other components. If some customer send me the two single row angular contact ball bearings in a pump without showing me which one is which and in which direction they were mounted, I can't perform a failure analysis. I just send them back. I must know which one was carrying the pump load and which one was the opposite, mounted in the opposite direction. If I don't have that information, you should never guess when you're doing this analysis. You must rely on facts. So now dismount the bearing using the most suitable method. Don't add additional damages that may affect the analysis. Check and measure the bearing seats. Look at the bearing seats. Do we have smearing or not? Check condition and lubricant distribution inside the bearing. Clean the bearing and now carry out the corresponding analysis. And again, I recommend compare with the photos shown on the ISO 15243 and photos published by bearing manufacturers, by SKF, AF, FAG, Timken, NSK, and so on. There are a lot of photos on the market that you can compare to see, oh, this is where, this is this, and this is that. You recognize it and you can determine exactly what was the cause. So if you have the cause determined, then you should have, and you can select the required corrective actions that should be taken. And don't throw the bearings away. Put anti-corrosion protection on them and store them. You may have similar failures in the future that you will be useful to. Oh, we had those bearings fail 2 years ago. How did they look? Nobody remembered, no photos were taken. But if you have those bearings in store as typical example, you may take them out and compare again and compare with photos and so on. And really be sure that the corrective actions you will recommend are the correct ones. So, doctors, excuse me, there's another example I will just show. But the most typical in my career is a large size bearing. Imagine a spherical roller bearing 241-900 CIK 34F. This is a 3.3 ton heavy bearing. You can see it here. It ran into a catastrophic premature failure. Look at this cracked in-ring. Look at the smearing of some of the rollers. It only lasted for 4 days to 105 hours. I love this example because it's a large size bearing with just a service life of 4 days due to 2 mistakes. The first one in the design area. they hadn't taken in account the extraordinary high dynamic forces. So the lubrication as such was incorrect from the very design. And then the customer, instead of applying the recommended special lubricant, sulfonate grease, 450 centistokes, they applied a standard EP2 grease. And so the failure was even further accelerated, and the bearing life was only 105 hours. Then the manufacturer of the in this case the cement mill and the bearing manufacturers together reviewed the design and changed over to a special designed oil for this application, and applied with circulating system, with filter and a cooler. And now this kind of cement mill is working just fine. So, good luck. And if you need some help, some assessment, and any courses, you will find me at proactivenews@gmail.com, bearing doctor and training. Thank you very much. And again, good luck. Bye.